hope everybody's having a wonderful day. We're going to solve rational equations today as opposed to just expressions. We'll do that in a couple of settings, and where we want to get to is where we can use this idea of rational equations in problem solving. That's kind of a powerful application of this. You'll use that quite a bit. Okay, so this guy right here, just to start, so now we're solving for x, right? We're solving. I want to know what x could be to make the left side and right side equal. I'm not just simplifying, I'm actually solving, okay? So, well, hey, we've been cross multiplying for a long time now, so we got x squared minus 9 equals 6x times x minus 3. Cross multiply. So x squared minus 9 equals 6x squared minus 18x. Set the side equal to 0 because we have a quadratic. 5x squared minus 18x plus 9. And, all right, tic-tac-toe again, because I want to factor that thing if I can. If not, I'll use quadratic formula, right? So we got 5 and 9. A and C multiply to get to 45. And then we add to get to negative 18. So 1 times 45, 3 times 15. Hey, bingo, 3 times 15. And they were both negative because they're adding to negative 18. Fill in our puzzle, and we've got turns out to be 5x minus 3 and x minus 3. So my solutions would be x equals 3, x equals, subtract 3, divide 3/5. All right, let's check those solutions, make sure that they work. Uh-oh, right here, 3 minus 3 would be bad. So this guy is extraneous. Sorry. So here is your solution right here. Okay? All right, now let's look at one where we don't have it set up quite so nice. We have to do a little bit of work to get our common denominator right here. So just like what we've been doing with expressions, we'll do the same thing with equations. 5x, 3x, and 3. The common denominator there is 15x. Okay? 5 times 3 is 15, and there's an x in a couple of those. So now, basically, I'm looking at each of these and saying, well, what would I do to get this to 15x? Multiply by 3 on top and bottom. What would I do to get this guy to get to 15x by multiplication? I would multiply by 5 on top and bottom. What would I do with this one? I would multiply by 5x. Okay? And the beauty of this is now we get 9 minus 20 equals 5x. Is my denominator is in effect gone. It has no bearing on, these are all 15x. Has no bearing on my solution for x. Okay? So now I got an easy algebra 1 problem. 5x equals minus 11. X equals minus 11 over 5. I just have to make sure that that doesn't cause any zeros in my denominator, and it actually makes the left side equal right side. It does both, so that's a good solution. Okay? So again, the beauty of this is we already have the skill of making a like denominator. If you've been doing your work the last few sections, you're going to be fine with this, okay? So now we're making a like denominator and using that to create our solution for x, right? We have an equation, not just an expression. All right? So let's go ahead and move into a couple word problems here, okay? Put our science cap back on for this one. Josephina is rowing. She can row 4 miles upstream in a river in the same time it takes her to row 6 miles downstream. Her rate of rowing in still water is 2 miles per hour. Find the speed of the current. We'll call that C. All right. So basically, her distance equals rate times time. That's your old science formula, right? And in this case, she can row 4 miles upstream in a river in the same time. Same time. Times are held constant. So how am I going to use this formula? I'm going to go distance over rate equals time. And I'm going to set her upstream equal to her downstream. Because she covered the same distance going both ways. This is kind of like our bike trip to Akron again, okay? So we've got so upstream against the current, she goes a total of 4 miles. The distance is on top here, right? Upstream is against the current. That's what upstream means. Okay. Uh, her rate is 2 miles an hour in still water, and if she's against the current, well then the current is subtracting from her speed. Agreed? Okay. Now, downstream, she went 6 miles was her total. Okay, 6 miles was her total. And again, in still water, she's going 2 miles per hour. But now, oh, glorious day, the current is at her back. It is helping her. It is helping her. And now we just have an easy little proportion to solve. And I get 8 plus 4c equals 12 minus 6c. And I get, keep going here, I get 10c equals 4. And the current is 4/10 of a mile an hour. 4/10, 2/5, and that's in miles per hour, right? Okay. But the key to solving this problem lies in the fact that you have to getting it set up correctly. Okay. Josephina goes downstream or 4 miles upstream in the same time it takes her to go 6 miles downstream. So you have to have something to set this equal. So this is like number one. It's still a proportion problem, but uh, it goes pretty quickly and easily once you get it set up. All right. Let's try one of these in the form of another problem setting. So Jim and Alberto, they're painting 600 square feet of hallway in an office building. Okay. All right. So they're going to paint 6,000 square feet. And working together, they complete the job in 15 hours. So the 6,000 square feet, that's one hallway that they get done together. Okay. Well, if they're working together, they're going to add their forces of work. Their okay. So basically, I've got two workers here. If they were working alone, they would complete 6,000 square feet. Okay. And let's say worker X amount of time it takes one of the workers to get it done. Actually, I'm going to call that the time it takes Alberto. He's quick, right? He's quick, all right? If he did it by himself, it'd take him a certain amount of time. And then, well, our pokey boy Jim here, it would take him, whatever it took Alberto, it would take him twice that. Okay? whatever it takes Alberto, it takes Jim twice that. But now together, we already know they work at, well, I don't want to erase that yet. 6,000 divided by 15, it they work at 4,000 or 400, excuse me, square feet per hour. Okay? So now we just have an equation that we're going to solve for uh, for x, really. Okay? So let's go ahead and do that, and then we'll be done. All right? So now the common denominator is going to be a couple ways of doing this. If I make this 400 over 1 instead of the 6,000, my common denominator is 2x. Okay, so I'm just going to write that over there, 2x. All right, so now I've got, to get this to 2x, this first right here, I'm going to multiply by 2, so 12,000. Okay, plus uh, 6,000 over 2x equals, this was 400 originally, so multiply by 2x on top and bottom, I get 800x over 2x. So now again, just like in our example number 2, the denominators are gone, and I get 18,000 equals 800x, and 18,000 divided by 800, okay, is x, the time it takes Alberto. So these zeros cancel. 8 goes into 18 twice with 2 left over. So that's 2 more and 5. 22.5 hours is x. Okay? So bottom line here at the end of the day is Alberto takes 22.5 hours and Jim takes 45 hours if they were going to do it alone. If they were going to do the job alone, that's what it would take. All right, so now we can solve rational equations. We basically, again, this is a beautiful thing, right? That we can set these problems up and do them just by themselves like this without having to, so we can take good problem settings and set them up into an algebra setting and do the work. Okay, we'll work on these quite a bit. This will take us some time to make sure we can practice this and get this right. But again, at the end of the day, we can set up rational equations and work them through if they're like this or if they're in a proportion setting. And again, the idea is just to create a common denominator if I'm in setting like this, and just solve the proportion if it looks like this guy. All right? Hope you're having a great day, and we will talk to you soon.